In this lesson, we shall write A as a product of elementary matrices. Given A equals the matrix with the first row 1 and 2, the second row minus 3 and 4, we present a solution to this particular problem in a step-by-step fashion as follows. Right, so we have the following. Right, we have exactly the following steps that we follow to be able to write A as a product of elementary matrices, and we proceed as follows. Right, now we let the matrix A be 1, 2, minus 3, and 4, like so. With that mentioned, then we have that the matrix A can be written as what you call an augmented matrix, and it is the matrix 1, 2, minus 3, and 4, 1, 0, 0, 1. And we're able to make the following observation. The second row plus 3 times the first row, which is 1, 2, 1, 0. Right, and with this particular elementary row operation, we say 3 by 1, which is a 3 minus 3, 0. 3 by 2 is 6 plus 4, 10. 3 by 1 is actually 3 plus 0, 3. 3 by 0, 0 plus 1, it's a 1. Next, we then have 1/10 row 2, which is exactly 3 out of 10, 1 out of 10. Right, so in the end, then, we then have row 1 minus 2, row 2, giving us exactly a 1, a 0. Right, and then if you then say row 1 minus 2 by this, right, which is exactly now minus 2 by this, it's actually minus 6 out of 10. So that 1 minus 6 out of 10 is like 10 out of 10 minus 6 out of 10, giving us a 4 out of 10, like so. Right, and we also have minus 2 by this entry, which is minus 2 out of 10. Obviously, combined with the 0 is minus 2 out of 10. Right, and this is 0, 1, 3 out of 10, 1 out of 10. And as a consequence, then what we then have here is that we have the 2 by 2 2 by 2 identity matrix, or the identity matrix of order 2, which is 1 and 0, 0 and 1. We perform an elementary row operation, only one, okay? Because for it to be an elementary matrix, we need to perform only one elementary row operation on the matrix I2, and this is able to give us exactly row 2 plus 3 times row 1, and which is exactly 3 and 1, and this gives us exactly the first elementary matrix. Give us now I2, which is 1, 0, 0, 1, and we're able to get the next one, which is 1/10 row 2, which is 0, 1 out of 10, 1 and 0, which is the second elementary matrix. So right now, we actually obviously still are looking at the 2 by 2 identity matrix. And from this 2 by 2 identity matrix, we will be able to achieve an elementary matrix by just applying one elementary row operation on the identity matrix. And that this gives us what you call an elementary matrix. So that here would have exactly row 1 minus 2, row 2. And with that mentioned, this gives us 1 minus 2, 0, 1. It produces exactly the third elementary matrix E sub 3. And thus we're able to make the following observation. Right, thus we are able to write the fact that at this point, we have the first elementary matrix E1, which is 1, 0, 3, 1. The second elementary matrix, 1, 0, 0, 1, 10th. Right, and we have the third elementary matrix, which is exactly 1 minus 2, 0, 1. Okay, now we have this. But now what is then important is that we have the following observation to make. Moreover, we started with the matrix A performing the first elementary row operation, getting E1, the first elementary matrix. Similarly, we obtained the second elementary matrix and the third elementary matrix, and as a consequence, the result was the 2 by 2 identity matrix, which obtained here. We started with the matrix A, performed the row reductions until we got to I2, the 2 by 2 elementary matrix. Now, what is the meaning of all this stuff here? Right, so the meaning of all this stuff is that we actually now need to solve for A from this particular equation. We need to solve for the matrix A, and this means that we shall actually be in a position to have the following. Right, we would have our I2, then we'd have our E3 inverse. Right, we would have the inverse of the third elementary matrix here, like so. Next, would have the second, and then would have the inverse of the first elementary matrix, and this gives us A, like so. Like so. Right. And this means, hence, this is E1 inverse, E2 inverse, E3 inverse. Okay, if you multiply by the identity, obviously you would have that the matrices these matrices do not change, and now we can therefore write A as a product of 3 elementary matrices over here. All right, so what do we do? What we then do is we then proceed to obtain the inverses. So in other words, we would need the inverse of the first elementary matrix, which is 1 over the determinant of E1, which is 1 by 1, which gives us exactly 1 minus 0, and this gives us 1 over 1, which is 1, 1, and we have 0 minus 3, like this, which means that we have E1 inverse, which is 1, 0 minus 3, 1. E2 inverse, right? You actually say 1 over the determinant of this matrix, which is 1/10. You switch the order of these here, and you actually take the inverses of these 2 entries, and this means that the inverse, now 1 over 10, it's 10. 10 by this gives us exactly 1, 0, 0, 10. Third inverse is obtained as 1 over the determinant of this, which is 1 by 1, which gives us exactly, so 1 by 1 minus this gives us determinant 1. Right, switching the places of the 1 and the 1 and taking the inverses would mean E3 equals 1, 2, 0, 1. And we therefore have these inverses here as a consequence. Right, and we're able to make the following observation with this here. Right, we're able to say, therefore, the matrix A can be seen as what? Right, the matrix A can be seen as E1 inverse, E2 inverse, and we also have what we call E3 inverse. Right, and we have written them down and we write it again. So we have this one is E1 inverse, E2 inverse, E3 inverse. What is E1 inverse? E1 inverse is actually exactly the following. Right, so we're able to make exactly the following calculation. Right, so, and we know that E1 inverse is 1, 0, minus 3, 1. Right, 1, 0, minus 3, 1. So in other words, we write here E1 inverse. Right, E1 inverse can be seen as exactly that one. Let's just write it down. So with E1 inverse is 1, 0, minus 3, 1. E2 inverse can be seen as what? E2 inverse? 1, 0, 0, 10. E3 inverse? 1, 2, 0, 1. So that now in the end, whenever you have, so this is exactly what we got. But now what is E1 inverse? It's 1, 0, minus 3, 1. E2 inverse is 1, 0, 0, 10. E3 inverse is 1, 2, 0, 1. Okay, so this has allowed us to write A as a product of these three elementary matrices. But we need to check if this is correct. Right, we need to check if this is correct. And let us do a quick check of this. Right, so in performing a quick check of this, we actually will note something that recall. Right, so we recall that the matrix A is 1, 2, minus 3, 4. We also recall that from these particular steps here, we take this exactly and we multiply these matrices. And we actually obtained that A was written as a product of 1 and 0 minus 3, 1. 1, 0, 0, 10. 1, 2, 0, 1. You multiply this with that, getting a 1, this with that, getting a 0, this with that, getting a minus 3, this with that, getting a 10. 1, 2, 0, 1. This by that gives us a 1, this by that gives us a 2, this by that gives us a minus 3, and this by that would give us exactly a minus 6 plus 10, and that's exactly a 4. In other words, it is clear that we're given the matrix A with the entries 1 and 2 minus 3 and 4, and we're able to write the matrix A as a product of 3 elementary matrices whose product is the matrix A. And we've solved this particular problem step by step, and we're done. And we thank you all for joining us. It was an awesome, awesome problem to solve. Thank you, and goodbye to all.